Welcome. Today we will discuss what is sampling theorem. Let's suppose I have this signal x of c of t, continuous signal, and this is discrete signal. So how much time ts should be to sample this into this form? What should be the sampling time? What should be the sampling frequency to convert this signal into this form, or to sample this signal, and how many samples we have? All these questions are answered by sampling theorem. Let's suppose we have x of t signal and impulse train. If we convolve this signal with impulse train that I discussed in last lecture. So the sampled signal in frequency domain would be like this one. The signal in time domain multiplied convolution with pulse train in frequency domain. Continuous signal in frequency domain, convolution with pulse train with in frequency domain. So what is the formula of pulse train in time domain? It can be found using Fourier series. So Fourier series, here C of k is the Fourier coefficients. To find Fourier coefficient, we have the formula 1 over t minus t by 2 to t by 2 integration, and we have the signal is impulse train. So if we integrate impulse train over minus infinity to infinity, summation and then integration, the answer would be 1. So C of k would be 1 over ts. If we substitute this value in the formula, it will come out to be 1 over ts summation k is equal to minus infinity to infinity e power j 2 pi k t by t. So if we apply the Fourier transform on this continuous signal in time domain, in frequency domain, it will look like this, because this is the shift that I discussed in the last lecture, and this is the amplitude that has been multiplied there. So pulse train frequency domain would be like this one. If we substitute these two values in this formula, we will get this. If we further solve it, taking coefficients outside the summation and taking this convolution in, this 2 pi will be cancelled out by this 2 pi, and x of s omega would be 1 over Ts summation k minus infinity to infinity now the signal is being multiplied by the or convolved by with the pulse train. If we apply the shifting property of impulse function, that is, if we have x of t and we multiply, convolve x of omega with omega minus the shifting property says that it will come out to be only this one. The amplitude is been multiplied or varied according to the impulse. Amplitude is been multiplied according to the signal. So the final result would be like x of c omega minus k 2 pi over ts. So sampled signal will be like this one according to this. So what sampling theorem says that sampling theorem states that if we want to discover the signal, we should sample that signal at 2f max. The sampling frequency should be twice the maximum frequency in the signal. Let's suppose maximum frequency in the signal is f max. So fs, that is sampling frequency, should be twice the maximum frequency in the signal. If we want to reconstruct the signal, sampling frequency should be twice. What does it mean? It means that sampling time would be half the maximum frequency. If I just substitute 1 over Ts, so Ts would be like 1 by 2 f max, so it will come out to be maximum time period. So if we want to reconstruct the signal, the sampling frequency should be at least twice the maximum frequency in the signal. What does it mean? Suppose we have this signal in signal in frequency domain. This is f max. These are conjugates. and this one is DC parameter, DC component. So sampling frequency should be twice. So if we apply the filter at this one, if we sampled the signal by Nyquist rate, it is called Nyquist rate also, and the theorem is also known as Nyquist theorem. So if we apply the low pass filter, the original signal, that was this one, can easily be recovered. So what happens if we don't have this, if we don't follow this theorem, or we have sampling frequency less than maximum frequency in the signal? Then this thing will happen, and we cannot just extract our signal from by using low pass filter. If we apply low pass filter, then these components, these shaded components, those are the high frequencies of the other components, signal component will come, and we will have interference, noise, and if we apply this low pass filter from there to there, then we will lose this information. So what this overlapping is known as, this overlapping of the signal is called aliasing overlapping of the signal. Suppose this one. This is aliasing effect. So how can we overcome this aliasing effect? The first thing is just increase the sampling frequency. So what if we can't increase the sampling frequency? We will have to just apply low pass filter first, and add there. Then we have something like our original signal. So we can overcome aliasing by pre-filtering and post-filtering. So how this aliasing or sampling frequency is being done, and what is the effect of this, we will see in a detail in MATLAB in the next video. We'll implement what I said in this lecture in this video will be implemented in MATLAB in the next video, and I will show you how these things aliasing and sampling if effects. If we have undersampling, what will happen? If we oversample, what will be the result? If we don't follow Nyquist rate, what will happen? If we follow this, we can construct signal or not. All these things will be seen in MATLAB in detail. That's it for today's lecture.